Welcome to the session at NDC Oslo. It's great to see a packed room, even though I can't see much because there's like a lot of bright lights in my face. But so if you're in the front rows, I can see you. So yeah, thank you for waving. That's awesome. If you're in the back row, you can do whatever you want. I'm not going to see it anyway. So all right. So I have like very strict constraints. So if you see me being nervous, it's like I'm used to walking around, but there's like cameras on me, so I'll have to stay in this boundary, and I'll try to do my best here. We're going to talk about API security for the next hour. And actually, the opening slide I'm going to use here is something I've never had to do before, and it's kind of a weird thing, but there's supposed to be a national security alert coming up at 12, so your phone will start making like a lot of noise, and we'll be very distracted, and it's going to be awesome. So it's supposed to be a test, at least that's what they told me, so let's hope that that's actually true, and that things will go away as quickly as possible. But yeah, let's see what happens as we go along. It's going to be a unique experience for me as well, so we'll see how that goes. But the gist of it, it's not like security alerts. It's kind of in the same space, but we're going to talk about API security more specifically. And when we talk about API security, it's kind of important to realize that API security has been booming in the last couple of years, as in it has gotten more and more important. And part of it is because we're building more and more API-based applications. Like anything new you're going to build today is likely going to be API-based. We have a lot of exposed APIs. And it turns out that a lot of vulnerabilities are also very visible in API-based applications. We're also building more interconnected systems, so things just get more complex, and more complexity typically means more chances to make a mistake, to screw things up, and to create security vulnerabilities. And one of the things that highlights this is the OWASP API Security Top 10. So OWASP is this non-profit organization that has been around since the good old days, like when we're building PHP and Perl-based web applications, like, yes, those days. OWASP back then created this top 10 for about the 10 most dangerous web security vulnerabilities. And over time, OWASP evolved as well. Web applications became API-based apps and mobile apps and AI stuff and so on. And what we'll see in the OWASP organization is a lot of these dedicated top 10s, because not all web security vulnerabilities translate well into APIs. Like you don't really have cross-site scripting in an API-based application. However, you have other problems. And this OWASP API Security Top 10, it's a second iteration, so it's been around for like 5-6-ish years, right before the pandemic hit. And it highlights the 10 most dangerous or most common vulnerabilities in modern APIs. And these things are, it's not an exhaustive list of stuff to check and then you're good. It's kind of a starting point. Like, hey, if you're doing APIs, these are the things you really want to take into account. And that's why the slide is right here. I'm going to talk about quite a few of these issues, but don't worry, I'm not going to go over like OWASP Top 10 number 1 and all the way to 10, because trust me, if you do that, you're going to be asleep by item 1.5, and you'll be like, oh, and that doesn't work very well. So what I'm going to do instead is I'm not going to list them one by one. I'm going to talk about real-world cases. I'm going to talk about a smart scale app, like a scale to weigh yourself, and it has an app and an API, and it had some security issues as well. Actually, quite a few security issues. So this is going to be my how to screw it up example. I say that respectfully, but it's just a fact. This is how not to do API security. Then the second case study we'll touch upon is from Dropbox. And Dropbox is actually on the other end of the spectrum. Like Dropbox is a company that invests heavily in security. They have a very good security team. They know what they're doing. They spend a lot of resources on security. And even then, things tend to go wrong. And this is kind of the wake-up call to you as well. Like, hey, even if you're trying your best, you're going to make mistakes. It's going to fail at some point, and that's why I'm doing this talk. That's why I'm here talking about these vulnerabilities. Now, who am I? I'm Philippe De Ryck. I'm a security expert, and I run my own company called Pragmatic Web Security. And what I do is I did a PhD in web security, so I've been in security for a long time, like really deep into it. And since my PhD, I've been helping developers understand security, like trying to explain very complicated topics in a way that you understand, translate them into actionable advice, coding guidelines, best practices, just like I will do in the talk right here. So I do that through training. I did a 2-day workshop here at NDC Oslo, so some of you may have been there. I do that through consulting, online courses, and so on and so on. All right, I'm also a Google developer expert, which causes some confusion. I'm not employed by Google, but it's kind of an outreach program that they reward people that are contributing to the community. So I'm a developer expert for security because of the talks and the articles and all of the stuff that I'm doing. I'm not employed by Google. They just send me free swag every now and then, which makes both of us kind of happy. So that's, that's a good deal. And then I'm also a SecOpDev organizer. SecOpDev is a course, Secure Application Development. It's a course in Belgium, week-long course on application security. and it ran actually last week. So if I look a bit tired, that kind of explains why. It's a hell of an organization, but it's a very great course where we bring in speakers from all over the world to teach application security. All right, so if you ever need an excuse to visit Belgium, that course, which runs again next year in June, is the perfect reason to come visit us and enjoy beautiful culture and liquid gastronomy, let's put it like that. So, all right, about this talk, you can easily find me online. The talks are listed on my website as well. You'll find the slides there. You can also scan the code if you want to grab a copy of the slides, a PDF copy, just to keep that in mind as well. All right. Let's talk about API security, shall we? We have about 55 minutes to dive deep into API security, and I want to do that by starting to talk about server-side request forgery. Server-side request forgery is this kind of a weird issue. It's something that all of a sudden popped up on the radar, like, hold on, there's a massive problem here. It has resulted in major breaches, and it's kind of a hit or miss problem. Like either you have SSRF vulnerabilities and you have to deal with them in various ways. You'll probably have them in multiple places, or it's not an issue at all, and you're like, me, I don't care. In that case, well, I'll wake you up when we're done with SSRF, but if you really care about server-side request forgery, this is really important. So why does this matter? Server-side request forgery is a vulnerability where the attacker can trick or manipulate your server into sending a request from its origin. So the server will send a request to somewhere else, and that can allow the attacker to control certain actions or behaviors or extract certain information and so on. And this matters because all too often we think about our environments, our application environments, our architectures, our deployments as a secure versus an insecure version, right? So we have our firewall, our perimeter, our private networks or whatever. That's paradise basically, where everything is beautiful and sunshine and blue oceans and whatever. And then you have the dark outside world where the attackers live. And that's how we often think about application security as well. And we all do that. That's just the way things are. And that's essentially what we're really talking about with server-side request forgery. Because when we do that, an attacker is able to trick our server, our backends, into making requests. So what's going to happen is something like this. The attacker provides a URL one way or another. A very good example of how this happens is a webhook. Many applications these days have webhooks, where a user, one of your users, comes to the application and says, like, if something happens in your app, like an event, maybe send me a request on this URL. If that user is malicious, they can provide you a malicious URL. And at some point, something will happen in the application. You'll call the webhook. You're now calling a URL controlled by the user. That's the risk here. And why does this matter? Because the request is originating from within your secure perimeter. Secure perimeter. If that still exists. Let's keep that discussion for a different time. But that's the whole problem, because now all of a sudden the attacker controls where the request is going to, and they might be able to reach things on localhost. The things you thought of, like, yeah, nobody else can call this except my application, so we're good. We don't really need security there. Or internal services that are less protected because it's internal anyway, not reachable from the outside world, like the dark, gloomy place. You can't reach this internal service, so maybe security is a bit less relevant. We've all made that argument at some point in time. Whether it's a right argument or not, that's essentially what happens. And that is the danger of server-side request forgery. It's basically a gateway into your internal networks, your internal environment, allowing the attacker to send that request. All right? So how does that happen? What are the features that triggers this? Webhooks are one example. Other examples are, for example, features where the attacker gives you a URL to fetch an image. That's exactly what happened at Dropbox. They allowed branding with URLs, and you provide the URL like, hey, my logo stuff is there, and Dropbox would accept the URL, fetch the logo stuff, and load it into your configuration of your account. That's another example. Link previews. You often have, like LinkedIn, if you post something on LinkedIn with a link to like NDC Oslo, you drop it in, and LinkedIn is being like, ooh, a URL, and it's going to take that URL, fetch that, and show you like the little preview with an image and a short description and a title. That's a server-side request as well. So these things are quite common in modern applications. All right? When it occurs, your internal infrastructure is exposed, and it may cause quite a few problems in practice. All right. So how do we protect against that? That's kind of the gist of this talk. It's not like a depressing talk of, oh, all of this stuff can go wrong. It's kind of should be an uplifting talk, like, hey, here's how we can fix that in practice. But it's going to take a few steps to get there. So let's look at some examples. The example of fetching an image, what happened at Dropbox. Here's a legitimate URL that we want to allow. Like, this is legitimate data, and we want to load that image, and that's perfectly fine. Something like this is invalid. right? I mean, localhost port 8080, that's not going to be a valid URL. That's not something we want to allow. And ideally, when you're building security measures, you would like to go for an allow list approach, right? You would like to go to an approach that says like, hey, these things I know are good, these are allowed. Like, yes, you're allowed to do this, and everything else is blocked. However, for server-side request forgery, that's one of the cases where this actually gets flipped around, because in the example like this, or the example of a webhook, everything is allowed except your own stuff, like the stuff you don't want to be called. And that's where you have to turn the model around, and we're going to have to implement an approach that says like, hey, things go into localhost or like a local network or maybe a private network range. Yeah, we don't really want to do that for a webhook or for fetching an image, but things running outside on the internet are acceptable. And that is a different approach. All right, so how do we do that? Well, we take a URL. What do we have to check? We have to check that the host name of the URL, like the host part, points to not something we don't want to call, but something external. Shouldn't be too hard, right? I mean, why am I talking about this? Shouldn't be that difficult. Well, it turns out that parsing URLs is kind of difficult, especially when they're malicious, when some malicious user is crafting a URL that might confuse your application. And remember, this is what happened at Dropbox, which I'll show you in the next slide. So what's the problem here? URL parsers are in various places, and you have application code that's basically going to say, like, here's the webhook. I'm going to take the host part. I'm going to resolve that into an IP address and then check if that is a local IP address or maybe an external one. All right? And if you do that in your application code, you're going to be at the bottom, like Node.js, Perl, Go, PHP, Ruby, all of those languages, and they will see a URL like this with 2 @signs, which is maliciously crafted. It's not supposed to be like that, but an attacker can provide that. And those languages will resolve this to google.com. And you're going to check this and like, yeah, that seems legit. Bam, and you will send that request to that server. Except when you send the request and you use a library to do that, and one common library is libcurl, which is hooked into many programming languages as well. You use curl or libcurl to send that request. It's a different URL parser with a different interpretation. It's going to be like, ooh, this request is going to go to evil.com. So you checked it, you said it's safe, you sent the request, and it actually goes to, well, evil.com or internal localhost or internal addresses and so on and so on. And you're now victim to a server-side request forgery attack. Just like that. You did nothing wrong, except, well, no, I don't think we can blame developers for this. This is just a weird piece of behavior in URL parsers, and there's a couple of these bypasses known today. Exactly what happened at Dropbox. So the Dropbox case with server-side request forgery, they were like, okay, we have to check where the request is going, and they actually checked that, but what they did is they used one application logic function to check it, that's the top one, which saw this URL, dlweb.dropbox.com @127001, and they thought, yeah, this is going to our servers where the images are hosted, this is perfectly fine. And then they sent the request using libcurl, and libcurl saw this as 127001, and we had that exact vulnerability, that exact bypass. That's how these things come to life and how they manifest themselves in applications. All right, so how do we fix this then? What's the actual solution to this? And the solution to this is to avoid parsing a malicious URL twice. What we really want to avoid is taking that untrusted URL from the user, parsing it here and parsing it there. If you only do it once, there's no confusion anymore. Because you see it once, you can reason about that one representation, whether it's good or not, either reject it or accept it, and from that point on, you use that accepted representation and the problem goes away. And one of the ways to solve that is by doing this on the server, by creating a safe URI first. So you get some input. I actually have some code examples. This is the Dropbox case, but I actually have some code here as well. So we remove ambiguity on the server by accepting the URL as input. We parse it using the URL parser. This is Node.js code. We parse it using the URL parser, and we use that representation to construct a new safe URL. And whatever the parser sees, that's what we will use as the URL. All right? Of course, you still have to do input validation to make sure the URL is valid, it points to a host you want to accept, and so on and so on. But that's how you remove the ambiguity. Parse it once, and then use that view for the rest of the application. All right. We can also move this towards the client. You can actually force the client to do this for you and only accept a decomposed URL. How does that work? Well, in this case, it's a browser-based application, so the front end running JavaScript in the browser would parse the URL provided by the user. So the user still enters the URL in the input field, we take that value, we parse it on the browser, and we decompose it into the different parts. And that's the data we submit to the server. So on the server, we don't get a full URL, but we get a scheme, a host name, a port, a path, and so on and so on. And each of these values becomes easier to reason about. There's no ambiguity. I mean, the host name, there's not going to be confusion like, is the host name this value or that value? No, it's the exact string that you get as the host name value. And you can input validate that like, no @ signs please, and so on and so on. And then you can verify that this points to a trusted location or something that you actually want to call, and you can accept this as input. And that's how you would protect against server-side request forgery. Remove the ambiguity, and then you can reason about that one representation to make sure it's a safe and trusted value. All right. Brings us to takeaway number 1, protect against server-side request forgery. That's kind of the important takeaway here. Server-side request forgeries, vulnerabilities often occur whenever you have a feature on the server that calls external hosts. All right, can be very visible, like webhooks, can be somewhat invisible, maybe hidden in libraries. We have seen this in PDF generation libraries as well, where you accept like a document and you generate PDFs from that. It can also trigger the sending of external requests. All right, the best thing you can do is ensure that this is trustworthy data, that it's unambiguous when you accept URLs. And then additionally, you can also isolate those features in like separate services and shield them off from your internal infrastructure. But that's kind of an advanced defense in depth approach to this problem. All right, that was one of the items of the OWASP API Security Top 10. Now for the second item, I want to talk about broken authentication. And broken authentication is this very generic item, and it has to do with all kinds of vulnerabilities that essentially result in the taking over of a user's account. And it can manifest itself in 1,000 different ways, and one of the perfect ways to describe this is using this smart scale application. So in this case, the smart scale application, I'm not sure if the scale itself was decent, but the API behind it definitely wasn't. And it had this abuse case where you could abuse the forget password functionality to take over an account. So all you need is like an email address of a legitimate user, and then you can forget the password for that legitimate user, and all of a sudden you can break into the application by taking control of that specific account. And to explain this, what I'm going to do is I'm going to use a demo, a live demo, so it's always a bit risky, but it should be fine. I'm going to do this live demo on breaking authentication. I'm going to walk you through a bunch of steps, explain how attackers come after your application, show you how easy it is, and also show you a couple of things you can do to defend against this. All right, let's see if we can actually get this to work. All right, what I'm going to do is I'm going to use a tool called Burp Suite. And Burp Suite is what pen testers and attackers also use to target your application. So in Burp Suite, you actually have one of the features there. It's actually really awesome. It's a proxy, and that proxy allows you to intercept all traffic between the browser and the backend. So what we're going to do is we're going to open this browser that will channel all traffic through Burp, and we're going to go to the application. Okay, crap. I should have checked this. Yeah. I forgot to enable internet, so there's no styling, but it probably should work. We'll see if it breaks, as live demos should always do. So the application, it's a restaurant review application. You can log in, create restaurant reviews, and as a legitimate user, we can actually authenticate here. We can log in. It looks very pretty, I know. Awesome styling. We're authenticated, and we're now logged in as one of the users. We're a malicious user. We're exploring the application to see how it operates and if we can find some weak spots. Right? So let's see what happens here. So we can now go back to Burp, and we can look at the HTTP history. So you can see here that we loaded the application, and we called the login endpoint. And as you can see, we provided a username, my email address, and then a password, test1234. This is not a course on choosing secure passwords, so just ignore that. And this is a legitimate authentication. Now, what happens if we try to log in with a password that's wrong? We get an error message, login failed, please try again. It's like, okay. And what happens if we log in with an email address that doesn't exist? That's actually formatted validly as an email address. We get the same error message. All right, so let's inspect what's going on behind the scenes. What we have here is we have a failed attempt, and the message here is invalid email or password. Now, sometimes applications are a bit silly, as in they return an error message in the API saying like, hey, this user doesn't exist. And you're like, oh, interesting. Because now we learn whether users exist or not. And to compromise an existing user in the application, we have to find existing users first. We don't know who has an account. Maybe you have an account on this application, but we don't know in practice. All right, so do we have a different error message? This is one. And the second error, where we have a non-existent user, gives the same error message. So nothing is happening here. We can't really discern whether a user exists or not. That's good coding. So that's already awesome. Thank you for these sound effects. All right. If you have trouble staying awake, this definitely helps. So now that I have your full attention, what's going on here behind the scenes is, yes, we'll have some people that are a bit delayed with a notification, so this is going to go on for a few more minutes. But what we have behind the scenes is we have a database of users. We have passwords stored in a database, stored securely with a password hashing function and so on. But if you look at the authentication logic of the login endpoints, so what we have here, that's a login endpoint. We look for the user. If we can't find it, we give an error message. The message to the API is this one. It's the same as we give when the user does exist, but the password is wrong. So that's good. That's a secure coding practice. So if the user doesn't exist, we bail out and we give an error message. But if the user exists, we check the password. That's kind of normal behavior, right? That's how you're supposed to implement authentication. However, this operation, checking the password, is using a password hashing function. And a password hashing function is designed to withstand brute force attacks. In case somebody steals your hashes, they're not able to brute force the passwords of your users. So that's the whole idea of this. And that operation is purposely slow, meaning it will take at least half a second. If it's good, it should take at least half a second to verify, and that might be observable behavior. So what can we do? We can use a timing attack to figure out if the application reaches this part of the code, yes or no. So let's do exactly that. What we're going to do is we're going to use this request and send it to a feature called the intruder, a very ominous name, but it allows us to launch an attack against the application. And we define some fields we want to play around with. We want to provide values for the email address because we want to find out if a certain email address exists in the application. All right, so that's what we're doing right here. And we provide a list of payloads here. We can load a list of emails, which we got from underground forums like data breaches of Facebook Messenger, has like a whole bunch of email, like millions and millions of email addresses. So we're going to load a list with millions and millions of email addresses or something like that in our application. There's only like a few because millions would take a while in the demo and it would be very, very boring to see. And we're going to launch this against the application. So we want to do a timing attack. So we don't want to do concurrent requests, but we want to do one request at a time. So we can get like good results. So one request at a time, and we start the attack. What you see here is Burp having some UI issues. I don't know why it does that. But what you see here is we send a whole bunch of requests. We tried 7 different email addresses, and they all failed, which is normal because, well, we don't have the password for these users. Otherwise, it would be very, very easy. So what we can do now is enable the column response completed, which shows us the response times. And this is all running on localhost, so it's super fast. And you can see like response time, 1 millisecond, 2 milliseconds, blah, 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 800. Huh. That's interesting, 800 milliseconds. This is observable behavior. Even over the internet, if you have a good internet connection, this is going to be observable. And this means that the application has been calculating a password hash. So that's a very good piece of information because now we know that victim@virtualfoodie.com, which is kind of obvious here, but that this email address exists in the application. So that's called a username enumeration attack. And that's something that's very effective to find out a list of existing users. And email addresses can be harvested from the underground web, but you can also get them by guessing or constructing email addresses. If you're working at a company and like Pragmatic Web Security and your email address is philippe.deryck@pragmaticwebsecurity.com, then it's going to be very easy to go on LinkedIn, find like a list of employees and use their first name dot last name at something something to construct a list of email addresses to use as input for this type of attack. All right, that was phase 1 of the attack. So First, let's talk about a fix. How do we fix this? How do we avoid this timing attack? Well, this operation should take as long as this operation. And one of the ways you can do that is, the easy way, is to calculate a password hash for a non-existent user. This is maybe not the best approach because it's expensive, as in it consumes server-side resources, but we can now calculate a fake password hash even if the user doesn't exist, and that will basically take as long as the other one. So let's see the effect here. If we launch the attack again, the UI is working correctly now. You can see that all of them take a long time, and we can see that the response completed is all about 800 milliseconds something. So this becomes unobservable. You could also do this with like a sleep or a delay somewhere, but this one shows you the effect of having constant time effects. All right, we're timing these really good, by the way, so let's keep doing that. All right, now we know that the user exists. So how can we take over that account? That's the ultimate goal here, account takeover. So what do? We want to abuse that account, and one of the features we can do that is in the nature of the smart scale, the forgot password feature. So we forgot our password, so what has happened, we enter an email address and we reset the password. And we get like a message, hey, we have reset your password, and you can now recover your account. How do we do that? By going to our webmail, webmail.restograde.com. We can reset the password by clicking this link. And that's how a lot of applications do this. You get like this password reset code, and with this unique code, you can reset the password for your account. Right? So we can click this. We end up here. We can set a new password. I'm going to use the name of my dog, Fluffy, my non-existent dog, by the way. Don't use this as my real password. It doesn't work anywhere. But Fluffy, we reset the password, and we can now log in with our new password, which should be Fluffy. And off we go. We're logged in, and we're all good. So what happened behind the scenes? Behind the scenes, we still have our proxy running. We requested our password reset. So we provide an email address to the API, and it says like, yeah, okay. We've basically meaning that we've sent an email to that user. Now, if we provide victim@virtualfoodie.com, we can't access their email. That would be too easy. We can't access their email, so we can't get their unique code to reset the password. So how do we actually reset the password? Here's where we load the HTML page. Here's where we reset the password. We provide that unique code and the new password, and it says new password is set for Philippe. All right. This is something we can abuse, right? It's a 4-digit code. How many options are there? Not that many, right? Something around 10,000, and we should be good to go. So let's, not a fictional example, by the way. This has happened in a smart scale application. This has happened in beta versions of Facebook and Instagram, where they had like production data with actual accounts and then no rate limiting on this endpoint. So making all of this possible. So how do we do that? Well, let's launch the attack again. First, as the attacker, we go here, and we're like, hey, application, we forgot our password. Our email address is victim@virtualfoodie.com. Reset password. Okay, mail has been sent. We can't access the email, so now we have to break the application, and we do that as follows. So we reset the password, send that to the intruder. We want to provide a code and Fluffy as a password, because why not? And we don't know what this code is, so we'll guess it. It's not going to be that hard. We guess for numbers. The number should be sequential between 1 and 99999. That's step 1. We want 4 digits and 0 digits behind the comma. So that's what we'll get as payload. That looks pretty good to me. What else do we need? Doesn't matter, but let's turn it off. URL encoding, we don't need that. That should be good, right? We want to use as fast as possible, 10 concurrent requests, that's fine. And then we can here look for this sentence, like new password set. If we find that, we have succeeded. So we can do that right here. We can match for this, clear the list, and add new password set. All right, let's see what this does. We can launch the attack now. I think I've covered everything, so let's see. We can launch the attack. You can see it's sending like requests sequentially, 1, 2, 3, 4, 5, and so on and so on. Here's the column, finding our results. And if we sort it, we find a 1, a match. And you can see the request 4769, and the response is new password set for Valerie, which is victim@virtualfoodie.com. So now we've taken over the account. We can log in with this information, so we can go to the application. We can go here. We can log in with victim and the name of my non-existent dog, Fluffy, and we're now authenticated. That's how we do account takeover. This happens in practice. This is super, well, as you can see, this is not a complicated attack to execute. You just have to remember to set parameters correctly, and then you're good to go, basically. All right? So how do we fix this? Well, there's a couple of things you can do. First of all, you should have rate limiting. I mean, it makes zero sense that there's an endpoint with a 4-digit code that you can just send like 10,000 requests to, and it's like, good enough for me. So rate limiting is very important there. Second thing is, maybe the 4-digit code is not the bestest idea either. You want to use like a long random string and something that is a bit more hard to guess. But the third thing I really want to talk about is why on earth do we allow guessing in the first place? I mean, this makes zero sense to just have like a parameter that the attacker can control and tamper with and try to attack. If we take that away, then this whole attack just goes away. I mean, it becomes impossible. And the way to do that is by adding integrity to that data. Because our application is providing that code and is receiving that code, we can sign that code and detect tampering with that value. And the way to do that is here. I'm using the generate reset code function from the insecure file, and I'm going to use the secure file, so this is super easy development. But what we're basically doing here is this reset code was a 4-digit number, and this one is a signed JSON Web Token. So what we're basically doing is we're creating a JSON Web Token. In the token, we add the email address of the user we're trying to reset the account for, and we sign that whole value, meaning that nobody else can change the email address to something else and cause this attack again. So let's take a look at how this works. We can go back here to our browser. We can reset our own password and go to our webmail. And you can see that the password reset link is now something very long, and this something very long is a JSON Web Token. And this JSON Web Token, we can observe this in Burp. This JSON Web Token contains, to observe this, we actually have to do this. Password is now test, another very secure option. So now the code that we send here is that JSON Web Token, and inside that JSON Web Token, as you can see here, is the email address of the user, an issued at timestamp, an expiration timestamp, and a unique identifier. And all of this is signed and verified by the backend. So if you would go in here, it would change like philippe@restaurate.com with victim@virtualfoodie.com. The backend is going to be like, you have changed that. This is no longer valid. Go away. So the only way to actually reset your password is by using your legitimate token, which has been sent to your email and is only accessible to you as a user. So this takes away the attack vector, takes away the capability of the attacker to try and tamper with this value. And that's essentially how you can secure your applications. This applies to reset passwords, but also to all other kinds of cases as well. So what we see today is a lot of applications relying on the on parameters in URIs for security, just by hoping they stay intact, but by adding integrity to that, you can actually secure your applications in practice. All right. Some takeaways. What do we take away from this demo? First of all, attacker tools are awesome. You can play around with Burp yourself. They have a free version to play around with. There's also alternatives, like OWASP has a tool called Zap, which does something very similar as Burp, and there's plenty of other alternatives as well. I just like Burp. I've been using Burp for a long time, and I'm a big fan of that. So that's option number one, or takeaway number one. Second one, avoid leaking information. Like this username enumeration seems like a silly problem, but once the attacker has a list of valid users, it just opens them up for all kinds of nasty attacks, like spear phishing, targeted attacks, account takeover vulnerabilities, and so on and so on. And if you don't leak that information, you take away that problem, and it gets better. So that's something to definitely pay attention to. Note that sometimes you really don't care about this. Right? For example, if you're a social media application and your users' names are public anyway, then you don't really care about username enumeration because it's just a list on the website. You can actually get them from there. So in that case, it doesn't matter. But if you're doing something more private, if the list of users is not easily guessable, this is something to definitely take into account. Maybe you accept that risk and you're like, we don't care about that, but then at least have it written down somewhere that that's your assessment of this threat. Second takeaway, implement rate limiting. Like this endpoint that accepted just like endless requests for guessing this 4-digit code, that's an absolute bad idea. So implement some form of rate limiting to kind of stop this from happening. And then the third takeaway is mitigate guessing attacks by adding an integrity check to the parameters in the URL. That's a really good way to stop these attacks at the beginning to not even make it possible. You can also, of course, do things like include random identifiers to make it more difficult to carry out this attack, but just stopping the attacker from being able to do that in the first place is a really good idea. And you saw this in the example, using a JSON web token to sign a value. That's not a heavy lift. That's something that's fairly straightforward to implement. There's plenty of libraries that support something like that, and it gives you solid security properties. All right. That brings us back to the API security top 10. What about authorization? Authorization is kind of important, as evidenced by number 1 in the API security top 10 and also number 5 in the API security top 10. Like somebody's 15 minutes over time with the alert. That's if this was real, you're in trouble, by the way. Everybody else is running and you're like, what's going on? It's like, I don't know. So authorization, what's going on with authorization? It's an absolute horrible problem that plagues everyone. And in this case, the Smart Scale application has some authorization problems as well. This application is kind of a gift that keeps on giving when it comes to security demos. It's yeah, there's just no end to it, basically. It's going to come back later again, so don't worry about that. Let me ask you what happened here? Well, the application allowed any user to add family members to any family. Like you're supposed to add a family member to your family. That's kind of designed feature. But if I'm a malicious user, I'm like, hey, I'm going to add a family member to your family, which is like weird, but it's a stepping stone for another attack. So why is this so hard to get right? Why is authorization on the API security top 10 number 1? Let me walk you through the process of how people often implement authorization, which I wish was totally fictional, but is unfortunately based on me talking to developers during security assessments and seeing these things in practice. So what are we doing here? I have created like a recreation of the Smart Scale problem. We have an add family member function. It's Java, so my apologies for that if you're a .NET developer, but everybody can read Java, so we're all good. So what are we doing? We're adding a family member. We have a family, we have an ID, this is straightforward, right? And we implement role-based access control. What we're basically going to do is we're going to enforce that to do that, you must be the family owner. That's authorization in action. All right? That's how this starts out. However, over time, you'll get more something like this. You'll have not only the family owner, but also a parent and an admin and this and that and that. And that highlights one of the problems with role-based access control. Managing roles is hard. You'll end up with a problem that we call role explosion, which is a very dramatic name, but it basically means that you'll have a lot of similar roles that have permissions, and it becomes really hard to assess a security policy like this. It's hard to audit a policy like this. It's hard to maintain. And if you want to add a new role in your application, now you have to go through your entire code base and be like, or has role this, or has role this, and it's just a mess. And this is a very silly problem to have, but it's unfortunately a very realistic problem because RBAC is very widely supported across all languages and frameworks. To improve this, to make this more maintainable, more auditable, you can do like a very simple thing. You can add a layer of indirection in between, which we call permissions. So instead of mapping roles to endpoints, we map roles to permissions, and we map permissions to endpoints. And now, if you look at this code, if you have to audit this, you don't have to have the full model in mind, like which role can do what. You can check like, hey, add family member has permission, add family member, like, yeah, that makes sense. A security audit like this, easy and straightforward. Like, yes, API code makes sense. Step 1, step 2, what does the policy say? Like, oh, these roles can have these permissions. Like, yeah, that makes sense to me as well. And this very simple step, very silly step on PowerPoint, but very powerful in practice, actually decouples permissions, decouples roles from endpoints by adding permissions in between. That's essentially how we improve authorization, right? And at this point, you're thinking like, yeah, that wasn't that hard. Like, what the hell is wrong with the Smart Scale people? Like, why is this API security top 10 number 1? Well, what we've done so far is we added function level authorization, right? We added a check whether a family member is allowed to add a member to a family. So if I want to add a member to my family, I'm going to create like a post request /family/1 member with the data, and bam, new member is created. If I want to add a member to your family, I'm going to take this request in burp, I'm going to delete the 1, I'm going to replace the 1 with a 2, which is like a sophisticated attack. I'm going to send the request out, and all of a sudden, well, a 7 actually, I'm going to replace the 1 with a 7, and all of a sudden I'm creating a member in your family. Because we've implemented the check that an owner, me, can add a family member, that's good. Function level authorization, but we never checked which family I'm adding something to. and that's object level authorization. So missing functional level authorization, missing this basic check is OWASP API Security attempt number 5, but missing the check to which object you're adding something to or which object you're accessing, that's OWASP API Security attempt number 1. Broken object level authorization. And this problem is everywhere. You will find this with simple IDs like accessing a family. That's what the smart scale was doing, wrong. You'll find this with multi-tenant deployments where you have like a header saying like customer ID something something. Well, an attacker can be like, customer ID today is 35, bam. And it sends a request, and if your backend doesn't check that the user actually belongs to that customer, I'm now creating admins in somebody else's customer, taking control of that customer, and you're now in deep, deep trouble. OWASP API Security attempt number 1. All right, so how do we fix this? And that's where the things get a bit tricky. To fix this, you need to add additional logic, because depending on why the user has this add family member permission, you need to check certain things. Like it becomes something like, this is a mess, by the way. You get code like this, like, check add family member, and it's like, oh, why do you have that? Oh, if you're an admin, then of course you can do that. If you're a family owner, then we'll make sure that you're the owner of this exact family, and you have to add a check, and so on and so on. And this code is in no way representative of how you write actual production code. First of all, smiley faces are not good for exception handling, in case you're wondering. That's not how you do that, for one. But also, there's no deny by default being used, and so on and so on. This is a bad example. For all intents and purposes, this is not good. All right, I have that on the slides just to make sure that you understand this. This policy, by the way, is impossible to audit for security. You have to do this. I strongly recommend this exercise at your company. What you do is you grab a colleague from a different team, you bring them to like on a Friday afternoon, and you show them your authorization logic. And you're like, do you understand this? Does this make sense to you? And if they can't immediately say like, yeah, I mostly get the gist of it, if your code is littered with checks like this, they're going to be like, I have no idea, man. I don't know. And that means your authorization logic is not auditable, which means if you can't audit it, how will you know if it's secure? You don't. It's kind of a best guess, like I'm thinking this is good, until somebody finds that one check that you forgot, and bam, you have a broken object level authorization issue just right there. And trust me, I've been in that meeting more than once. And I ask questions about that, and I ask like, how do you check this, and where do you check? And people open up the code like, yeah, we have this here. And sometimes they go quiet and get like a bit red-faced, and sometimes they whip out their code editor and like, oh yeah, let's add this additional rule that we forgot, like on the fly. It's like, no, that's absolutely not what you're supposed to be doing. So how can we improve this? This is not the depressing talk about how miserable your life is supposed to be. This is about improving things and making things better for yourself. And a very simple thing here that you can do is you can centralize this logic. You can take away all of these dirty checks and move them into a single location. We call that the policy engine, which is a very that's how you sell this to your boss. Like, we need a policy engine. In reality, you can make this super simple. You can make this like one class, one file with static methods. And these static methods can be check permission or can add family member or whatever. But what we're doing here is we're making our endpoints prettier, easier to audit, and manageable. Because if you have to audit this code that you see on the slide now, all it takes is like add member, we check the permission, add family member, like, yeah, this makes sense to me. If I have to audit this, I'm going to be like, yeah, that's a good check. You can even add like rules in your linting tools or static code analysis tools that every endpoint has to call policy.checkPermission or the build breaks. Good, now you can't forget authorization checks. Perfect. Second step in auditing this, you go to that policy file and you check what are the rules that are enforced here. Do they make sense? Very important. Second thing you can do, you can enable version control, like source code protection on that file so that only the people from the security team are allowed to update this. Awesome. Third thing you can do, and that's really powerful, you can write unit tests against your authorization policy. Because all you have is these check permission or can add family member methods, and you can write unit tests to make sure that they enforce what you think they enforce. And that gives you a lot of power over your authorization logic and makes all of this manageable. And on top of that, it prepares you for the next step, because sometimes most people can get away with this. Most applications I've seen, they can get away with this and they're good to go. Easy, straightforward, cheap, perfect. However, sometimes you have this complex application, complex authorization logic. Maybe you have to check like a whole bunch of relationships to see whether this is possible, and that's where external policy engines come into play. That's where you want to externalize this authorization logic into something like an open policy agent or something custom or open FGA if you're using that, and where you check that authorization logic. And that way, now you have a real policy engine. Now you move it outside to an actual service, which uses, in OPA's case, Rego as an expression language to write your authorization logic. But that's the next step. That's an advanced use case. And to be honest, most applications don't need to go that far. You may want to do that. That's on you. That's perfectly possible. But very often, you don't have to go that far. Just centralizing the logic in your code base is enough for most use cases. All right, and that's the takeaway here. You want to centralize that authorization logic. You want to simplify the auditing of your authorization policies to ensure that you can keep everything under control and that you can assess the security of what you're enforcing. And that's the way how to fight broken object-level authorization. All right, second takeaway here is empower auditability. Make this possible. Do the exercise with your colleagues. It's super valuable to figure out or to observe how somebody else views your authorization logic. And guess what? If your colleague spends like an afternoon with you and they can't understand your authorization logic, then something is wrong. Maybe you picked the wrong colleague, that's also an option, but assuming that you have competent colleagues, the problem is with your authorization logic, not with your colleague. All right? Good. Let's talk about authorization, right? We talked about 1 and 5, but there's another authorization. Seriously, authorization is a mess. There's a third authorization issue in the OWASP API Security 10, and that's number 3, broken object property level authorization. And the abbreviation for that is BOPLA, in case you're wondering. And I don't know who makes this thing up, but it's broken object property level authorization. And guess who had that problem? Smart Scale, of course. Sorry if you're actually the developer of this. I don't want to do this, but it's just the way things are. So that's just the way things are. So what happened here? And that's the second step in the attack. So what the attacker really figured out is we can add family members to your family. And now we have an account that we control that's a member of your family, so we can authenticate as that account. And guess what we can do next? We can list the other family members in your family, which is kind of normal. That's, yeah, of course you can. It's like, yes, if you're a child, you can see your parents and your sister and brother, and it's like perfectly fine. Except the Smart Scale, when you listed the users, managed to expose like the full user object. Not just like a name and an age. No, the full user object, including access tokens and refresh. I don't even know why these values are in there, but they were, and everything was listed. And you're laughing, which is like, oh my fucking God, what the hell, sorry for the language, oh my freaking God, what the hell is wrong here? And I wish that I could say like, oh yeah, it's just a smart, nobody else is doing this, but it's everywhere. Even Uber had that vulnerability a while ago where they were leaking this information on user accounts. We've seen password hashes being leaked, location information being leaked that was known by the application. And location information, that's kind of a critical feature. Like many dating apps, they have location information. That's something you never ever want to leak to malicious users in practice. So yeah, this is a major issue. Why do we have that? Like, what the hell is wrong with us? Why do we create these vulnerabilities? Well, actually, we don't really create them. It's just the nature of the game of transforming data into JSON and so on, because nobody in their right mind writes JSON by hand. Well, maybe some of you are really miserable and you're like, yes, I write JSON by hand. But most people don't. And what we do instead is we translate model objects like a user that we have in our system, a model, and we translate that into JSON by telling the framework, here's the list of users, go figure it out. And the framework is like, yeah, awesome. It's a Java object, I can translate this property into JSON, and so on and so on. And we have something like that. And I have an example here, which is not the Smart Scale, but it's an API security swag shop where you can buy cool things about API security. And they have a list of online users. And the list of online users in the front end, it's based on the API response, like it calls to /online users, and it gets a list with user objects, like ID 5, ID 3, name John. And that's the information that we list there. And that's how these vulnerabilities come into life. They're not like in the front end. We're not displaying like all the information in the front end. No, the information is in the API response. So we call this endpoint, we get an API response, we take some values and everything else is ignored in the front end, but it's there in the back end. So somebody doing this attack, which goes as follows, like open DevTools in the browser, go to the network tab, click on the API request, look at the response, and poof, all the data is there. That's how the attack like this works. And I encourage you again, I have another exercise for you later on, to look at actual applications you use day in, day out. Open up an application like your banking app and go look at the API responses. The amount of data that's there is astonishing. It's crazy. I've done that and I was like, what the hell is going on? Like there's so much information that the front end never uses that we expose in API responses. That's exactly this problem. That's what's going on. So where do we get that from? Here's another, okay. Yes, here's another example. Again, it's Java, but whatever. What we do here is we get a list of online users. It's a list of an array of user objects. You kind of know how this works. It's a list, sorry, not an array. And we throw that into the response, and magic happens, and JSON comes out. And you can see the user on the left. We have the name and the address, and we're exposing the address information here, or the access token and refresh token, whatever the smart scale was doing. That's how this happens in practice. So how do we fix this? We can annotate this with JSON ignore. Like, hey, JSON translator thingy, we don't really want to expose this property, so just pretend it doesn't exist, right? I'm not a fan of this. This is kind of a band-aid approach, like, oh yeah, whoops, this one shouldn't be exposed, but you can't scale this. You can't do this for your entire API. It's going to be a mess. You're going to forget fields. It's going to be a problem. So how do you do that instead? You use a DTO, right? A data transfer object. Or if your language doesn't have DTOs, you can have like schema validation and so on. That's a similar approach. And that DTO is now called public user info. And it makes it hard to make a mistake, because whenever you're writing this like public user info, you're not going to be like, access token, yeah, let's put it in there. No. It's going to help you remind yourself like, oh yeah, this is supposed to be public user info. And that way, we map our users to this DTO, we expose the DTO, and the problem goes away. All right? Very simple approach. Takes a bit of effort to do that, but it's recommended to do that effort because it really gives you strong security properties. All right. Now, I talk to a lot of developers. I work with a lot of developers, and this is something that very often comes up when we talk about API security. And they're like, yeah, we're using DTOs. And I'm like, okay, show me. Always ask them like, show me. That's very important. Just using DTOs itself? No, show me. And it's like, yeah, here's the DTO. And I'm like, okay, where do you get it from? Well, it's a DTO with a lot of properties. And I'm like, where do you get this from? Yes, we auto-generate this from our model classes. Like, the model translates automatically into the DTO. It's like, that's not what you're supposed to be doing. And you can do a similar thing with OpenAPI specification where you define exactly what you expect and so on. And I was talking about this at a workshop last week, and somebody phrased this very accurately, so I'm going to steal that and use that from now on. And he said, like, yeah, somewhere in the process, somebody has to do the thinking. Like, somebody has to be thinking, like, what do we want to expose? Because all of these automatic generation tools are awesome, but if you generate your OpenAPI spec from your DTOs or from your model classes without ever thinking at some point, like, do we want to expose this, you're going to have a bad time. That's essentially what's going on. So what you're supposed to be doing is you're supposed to be using DTOs, but either if you auto-generate them, you have to manually review them. You have to go through and check if this makes sense. But my advice is do not generate them, write them yourself, because you'll have different versions of a DTO. Like admin users will see more properties than a regular user, and so they have separate DTOs with separate sets of fields that are exposed. Do the thinking. That is essentially, I should add that as a takeaway slide. I haven't done that, but do the thinking. That should be the main takeaway from this part. But in this case, it's avoid sensitive data exposure. You have to go through. I'm very certain, we have a full room here, like a few hundred people. If you go through APIs, I'm fairly certain that you will find quite a few of these instances. That's how common these things really are. And they're invisible, mostly. Unless you go look at your actual JSON responses, you won't see this at all. Until somebody finds this and you get embarrassed in my slides because you're now one of the stories. So that's essentially how that comes into play. Now, there's a write version of this vulnerability as well. So this is the read version where you expose too much data, but the same goes on. I don't have slides about that because I'm running out of time, but the same goes on with the write version where the user provides more properties than you expect and you overwrite these fields in the database, and that's called mass assignment. And it's also part of broken object property level authorization. All right, and the same defense applies. You use DTOs there to avoid accepting more information than you should, and that is essentially how you solve this problem. All right, so it's getting rough up here on stage because the pizza stand is below and it's smelling delicious, so I'm super hungry. But let me come back to this OWASP API Security Top 10. We talked about quite a few of these issues. These things are there for a reason. All right, the fact that a broken object level authorization is number one, it's not because this is the odd case in a smart scale, it's because this is everywhere. So please take this away from this application. Go look at your APIs, probably on Monday, because it's a 3-day conference, so that's perfectly fine. But go back to your APIs on Monday and review your authorization logic for these things. Make sure you can improve that. All right, key takeaways. What did we learn here, or what do I think you learned here? Let's put it like that. The best authorization policy is understandable and auditable. Like if it's complex and scattered throughout the code, it's going to be a mess. It's going to be really hard to protect or to assess whether it's secure. Make it understandable. Really, really important. The easier it is, the better. Analyze your APIs for data leakage and brute force attack vectors. These are, again, very common, something you definitely want to look out for. And keep in mind that perimeter security cannot be your only defense. Perimeter security is good. You should shield things as much as you can, but be aware that attackers have ways to breach the perimeter in legitimate purposes, like server-side requests or loading like a page in a browser from within the perimeter. All of that is enough to give the attacker a foothold within the perimeter. Make sure you have additional defenses at play that prevent this from being abused. All right, if you liked what I had to say here, I'm actually doing that 2-day workshop I did the previous days in the future NDC events. So if you want to go to Copenhagen or Porto, very tough place to be at, Porto, or NDC Security here in Oslo next year, feel free to sign up and I'll see you there. And with that, I want to thank you, enjoy the pizza, and have a great conference.